In this lesson, we're going to continue our work on solving inequalities and looking at the graphing connection and looking at solving inequalities that have absolute values in them. Um, so let's take a look at this one with a graphing connection first. If you look at this inequality, negative 3x plus 5 is greater than or equal to 2x minus 10, you can see that this left side of the inequality could be the equation of a function, and same with the right side. So what if we put those into our calculators where y1 is negative 3x plus 5, and our second function we can enter as y2 equals 2x minus 10. Let's put those up on in our calculators and see what happens there. So I've got negative 3x plus 5 and a second equation of 2x minus 10. And I just want to make sure I'm zooming. 6. So there's the first equation and there's the second equation. I'm really looking at when is this first equation greater than or equal to the second equation. And you can see on the right side of the graph here that on the left side of the graph here that the first equation is greater than the second equation really in this whole area here, because here's the first line and it's greater than the second line. Okay? So that's the way to think about it with graphing. So you can think of when is y1 greater than or equal to y2. So we can also do it though by rearranging the equation. So if we look, or the inequality, sorry. So if we look at this original inequality, and let's add 3x to both sides, I end up with 5 is greater than or equal to 5x minus 10. I'll add 10 to both sides, so 15 is greater than or equal to 5x. We'll divide both sides by 5 and get 3 is greater than or equal to x, but we like to write that differently, so we'll write that as x is less than or equal to 3 as our solution. And if we go back to the calculator, you can see that from x equals 3 to the left, that's when that first equation was greater than the second equation. Okay, so that's a relationship between graphing and the solution to the inequality. And that process will be helpful as we look at absolute value inequalities as well. So let's look at this equation, or inequality rather. The absolute value of x is less than or equal to 4. So one thing that we could do is look at the graph of that. So if I bring back up the calculator and erase the marks on here and go back to y equals and clear both of those equations out and instead go to the absolute value of x. So remember that's math and going across to num, and number 1 is the absolute value. So the absolute value of x, close the bracket. So let's graph that. Okay, there's that familiar V-shaped graph, and we want to know when it's less than or equal to 4. So if you think about the values here, 1, 2, 3, 4 is up here. So there's where it's equal to 4, and here's where it's equal to 4. So this whole range here is when it's less than 4. Outside of that, it has a higher value than 4. So you can see that there's an interval where it's less than or equal to 4. Okay, the other thing we could do is we could go to the calculator and we could put in a second equation. Just erase that a second. We could put in a second equation that was just y equals 4, which remember gives us a horizontal line. So you can see that the absolute value function is less than 4 for that interval that I had highlighted earlier here. Okay, so and you can see that it's the values from -4 up to +4 that it's less than or equal to. So our solution is actually -4 to +4. Okay, and if we go back to the graph and look at when is x, I'll just call this part B, the absolute value of x greater than or equal to 4. I'll bring the calculator back up here. When is it greater than 4? It's off here to the left, which is the interval. Don't know why I wrote the number 5 down there, but it was that interval from -infinity up to 4, up to -4 rather. But also, you can see it's the interval from that goes beyond 4 as well, that we're greater than 4 there as well. So we call that, we can do that as a union of the interval from 4 to infinity. Okay, so there's two parts to the interval. One is -infinity to -4, and the second one is 4 to infinity. And that's where the absolute value of x is greater than or equal to 4. So being able to visualize an absolute value function is really helpful to recognize why you have an interval with two boundaries in this first case and two intervals joined together in the second case for a solution to that inequality. So these are the steps um, to solving an absolute value inequality using boundary points. So for example, the absolute value of u is less than or equal to c, and c is some constant. If we look at this original one, we've got the absolute value of x is less than or equal to 4. Where did it cross? What were the boundary points of that function? And if I just do a rough sketch of it here, it was, the function goes like this, and when is it less than 4? At these two spots, and this one was this point 4, 4, and this one was the point at -4 and 4. So the boundaries were really -4 and +4. Those are the boundary points, okay? And then, so that would be the first step, is to figure out the boundary points, then locate them on a number line to find the intervals to test, choose a test value inside each interval. If the test value leads to a true result, that interval is included. If the test value leads to a false result, the interval is not part of the solution, and then write down the solution set, which may include one or more intervals. That sounds like a lot. Let's just go through the steps with this next question here. Okay, so here's an absolute value inequality. And let's go through the steps of solving it using the idea of boundary points, okay? So if the absolute value of 2x minus 3 is greater than or equal to 11, the first step is to solve it as though it's equal to 11. So if I have the absolute value of 2x minus 3 equals 11, then either 2x minus 3 is equal to 11, or 2x minus 3 is equal to -11, right? So if you think about if the absolute value of something equals 11, either that something is 11 or it's -11 by definition of what absolute value means. So let's solve this little equation on the left here. So I'm going to add 3 to both sides, so 2x equals 14, divide by 2, and I'll have x equals 7. If 2x minus 3 is equal to -11, I will add 3 to both sides, so I'll have 2x equals -8, divide both sides by 2, and have x equals -4. So those now are considered my boundary points. So let's take a look at a number line with those points on it. So there's 0, there's 7, one of my boundary points, and 1, 2, 3, 4, there's -4, the other boundary point. So the number line is split into three intervals. The first interval is everything to the left of the -4, so it's the interval -8 to -4. Then the next interval is the space between these two values. Okay, so from there to there, and that's the interval -4 to 7. And I see I wrote my infinity symbol wrong there. Let's fix that up. So that's an infinity, not an 8. And the final interval is that piece beyond 7. So that's the interval from 7 to infinity. So I have three sections on the number line, and I'll test a value that's in each of those three intervals to see which ones are part of the solution set. Let's scroll down to give myself some working space here. So in the interval from -infinity to -4, I want to test some value in there. So test a value from each interval. So let's, for -infinity to -4, let's just test the value x equals -7. Okay, and we'll test it in the original inequality. So the absolute value of 2x minus 3, so 2 times -7 minus 3 is greater than or equal to 11. So -14 minus 3 is -17, greater than or equal to 11. Well, that gives me 17, which is greater than or equal to 11. So that piece is true. So that means that that first interval is true. So the numbers in that interval make the original inequality true. Let's test a value from the middle interval now. The interval goes from -4 to 7, so let's test x equals 0, the easiest one to test. So we'll have the absolute value of 2x minus 3, so 2 times 0 minus 3 is greater than or equal to 11. So I have the absolute value of -3 is greater than or equal to 11. Okay, 3 is never greater than or equal to 11. That piece is false. So that interval, the values in that interval do not make the inequality true. So now let's try a value in the latest interval where it's from 7 to infinity, and we can pick any number in there. Let's just pick 36. So we substitute it again into the original inequality, so 2 times 36 minus 3 is greater than or equal to 11. So that gives me 72 minus 3, which is 69. Well, 69 is greater than or equal to 11. It's true. So that final interval is also good. Any value in that final interval is true. So our solution is going to be the interval from -infinity to -4, and I'm going to put a square bracket on it because the question was greater than or equal to. So I'll put a square bracket on there, and it's that set united with the interval from 7 to infinity, and again a square bracket because it's allowed to be equal to. Lots of steps there. So we can show that on a number line, and we can also show it using interval notation. If we do that on a number line, we will have the set, let me pop a 0 and a -4 and a 7 on there. We can show that set as being that set and this one combined, or we could write it in set notation using x is a real number such that x is less than or equal to -4, or x is greater than or equal to 7. That way we're taking care of both intervals in one set of set notation. Now, from the questions that we've done, this question originally was a greater than or equal to question, and we ended up with two intervals on the outside that were the solution, and the original one was the absolute value of x is less than 4, and it gave us just one interval, which was the middle one. So I'm just going to write that down. Did you notice? The absolute value of u is less than c leads to one interval. And the absolute value of u is greater than c gives us two intervals. And if you think about what the absolute value function looks like, and I'll just sketch it off to the side here, that makes sense. Even if that interval, even if that function is translated or moved somewhere else, you still have, when you think about it being larger than some number, you end up with two portions of that function. And if you end up with it being less than, you end up with one portion of it being true for that type of question. So, in conclusion, we can say that the absolute value of u is less than c. Okay, so when we've got a less than, and that'll include the less than or equals, so that'll be, are the values, the solution to that are the values between the two boundary points. So the values that satisfy negative c is less than u, which is less than c. And the absolute value of u is greater than c, are the values that satisfy u is less than negative c or u is greater than c. So when we've got a greater than, we end up with the two variables or two intervals, sorry, as a solution, and when it's less than, we have a one interval with two boundaries as our solution. So let's take a look at a question, because you'll see that this becomes a much simpler way of solving an absolute value inequality. We have 3x plus 7 is less than 19. So this is one of those less than situations. So we know that that absolute value then is, it's less than, it's the center interval. So we can really say that negative 19 is less than 3x plus 7, which is less than 19. So now we have a compound inequality. Just a second. So let's just isolate the x term here. So we'll subtract 7 from both sides. So I have negative 26 is less than 3x, which is less than 12. And then let's divide every term by 3. So we have negative 26 over 3 is less than x, which is less than 4. So there's our solution. It's the interval from negative 26 over 3 to 4. And we could sketch the graph of that as well. That's 0, here's 4, and negative 26 over 3 is approximately negative 9. So there's negative 26 over 3, and it's the interval that comes between those two. So, and it's because it's not equal, we'll use the rounded brackets on it. And we'll stop there for today.